What if I told you that somewhere in the universe, it rains diamonds, and on another world, the surface is so hot it could melt lead in seconds? The cosmos is filled with environments so extreme, they defy everything we know about life and survival. From the crushing gravity of black holes to the icy wastelands of distant dwarf planets, the universe is a place of unimaginable extremes. In this video, we're diving into 25 of the most mind-bending facts about the universe's most extreme environments. These are places where the rules of physics are pushed to their limits and where the very fabric of reality seems to bend. By the end of this journey, you'll not only gain a deeper understanding of the cosmos, but also discover just how strange and awe-inspiring it truly is. So, are you ready to explore the universe's most hostile and mysterious corners? Let's begin. Now, let's turn our attention to the scorching surface of Venus, a planet that takes extreme to a whole new level. Imagine a world where the average surface temperature is a staggering 870 degrees Fahrenheit, hot enough to melt lead in seconds. Venus, often called Earth's twin due to its similar size, is anything but hospitable. The reason for this inferno lies in its thick atmosphere, composed almost entirely of carbon dioxide. This dense blanket traps heat so effectively that it creates a runaway greenhouse effect, making Venus the hottest planet in our solar system, even hotter than Mercury, which is closer to the Sun. The pressure on Venus's surface is equally extreme, about 92 times that of Earth's. To put that into perspective, it's like being nearly 1 kilometer underwater in Earth's oceans. This combination of crushing pressure and searing heat makes Venus one of the most challenging environments to explore. Spacecraft sent to Venus have only survived for a few hours before succumbing to the planet's harsh conditions. For example, the Soviet Union's Venera probes, which landed on Venus in the 1970s, transmitted data for just over an hour before being destroyed. Exploring Venus isn't just about surviving the heat and pressure. The planet's thick atmosphere also obscures its surface, making it difficult to study from orbit. Unlike Mars, where rovers can roam for years, Venus requires entirely new technologies to withstand its extreme environment. Scientists are now developing heat-resistant materials and innovative designs for future missions, hoping to unlock the secrets of this hostile world. As we move forward, we'll explore another extreme environment, but this time we'll venture to the icy reaches of the solar system. Pluto, a distant dwarf planet, holds its own set of mysteries and challenges, proving that the universe's extremes come in many forms. Now let's journey from the blistering heat of Venus to the icy, distant reaches of our solar system, where Pluto awaits. This dwarf planet, once considered the 9th planet, is a frozen wasteland unlike anything else in our cosmic neighborhood. With surface temperatures plunging to a bone-chilling negative 375 degrees Fahrenheit, Pluto is so cold that even gases like nitrogen and methane freeze solid, creating a landscape that feels almost alien. Pluto's surface is a patchwork of icy plains, towering mountains, and vast glaciers, but these aren't made of water ice like those on Earth. Instead, they're composed of frozen nitrogen, methane, and carbon monoxide. One of the most striking features is Sputnik Planitia, a massive heart-shaped glacier that stretches over 620 miles wide. This icy plain is thought to be constantly reshaping itself, with nitrogen ice flowing like a slow-moving river driven by Pluto's faint internal heat. But Pluto's icy wonders don't stop there. Scientists have also discovered evidence of cryovolcanoes, or ice volcanoes, on its surface. Unlike the fiery eruptions we see on Earth, these cryovolcanoes spew out a slushy mix of water, ammonia, and methane, which freezes instantly in the frigid temperatures. These features suggest that Pluto might still be geologically active, with a warm interior that occasionally breaks through its icy shell. What makes Pluto even more fascinating is its thin atmosphere, which is primarily nitrogen with traces of methane and carbon monoxide. This atmosphere isn't constant, it freezes and collapses as Pluto moves farther from the Sun, only to reform as it swings back closer. This cycle creates a dynamic environment, adding another layer of complexity to this already mysterious world. As we continue our exploration of the universe's most extreme environments, we'll next turn our gaze to the heart of our galaxy, where a supermassive black hole reigns supreme, bending space and time itself. But for now, Pluto stands as a testament to the incredible diversity of worlds that exist in the far reaches of our solar system. Now, shifting our focus from the icy plains of Pluto, let's venture into the very heart of our galaxy, where an unimaginably powerful force lies in wait. At the center of the Milky Way, approximately 26,000 light-years from Earth, sits Sagittarius, a star, a supermassive black hole with a mass equivalent to 4 million suns. This cosmic behemoth is the anchor of our galaxy, its immense gravitational pull shaping the motion of stars, gas, and even light itself. Sagittarius, a star, is not just a black hole, it's a gravitational powerhouse. Its influence extends far beyond its event horizon, the point of no return where not even light can escape. Stars orbiting close to Sagittarius, a star, whip around at astonishing speeds, some reaching velocities of thousands of miles per second. These stars, caught in the black hole's gravitational grip, follow elliptical paths that bring them perilously close to the event horizon, offering scientists a rare glimpse into the extreme physics at play. But the black hole's impact doesn't stop there. Surrounding Sagittarius, a star, is a swirling disk of superheated gas and dust, spiraling inward as it's pulled by the black hole's gravity. As this material gets closer to the event horizon, it heats up to millions of degrees, emitting intense radiation across the electromagnetic spectrum. Occasionally, the black hole devours large clumps of gas, creating spectacular bursts of energy that can be observed from Earth. These outbursts provide valuable clues about the behavior of supermassive black holes and their role in shaping galaxies. What makes Sagittarius a star even more fascinating is its relatively quiet nature compared to other supermassive black holes in the universe. While some black holes are surrounded by bright, active regions known as quasars, Sagittarius, a star, is more subdued, only flaring up occasionally. This calm demeanor has allowed astronomers to study it in detail, revealing insights into how black holes interact with their surroundings and influence the evolution of galaxies. As we continue our journey through the universe's most extreme environments, we'll next explore the intense radiation storms of Jupiter's magnetosphere, a place where the solar system's largest planet creates a hazardous zone unlike any other. But for now, Sagittarius, a star, stands as a reminder of the incredible forces that govern the cosmos, hidden in plain sight at the center of our own galaxy. Now, let's turn our attention from the quiet yet powerful Sagittarius, a star, to a place of relentless chaos and danger much closer to home. Jupiter, the largest planet in our solar system, is not just a giant ball of gas, it's a radiation powerhouse. Its magnetosphere, a vast region of space dominated by Jupiter's magnetic field, is one of the most extreme and hazardous environments in our cosmic neighborhood. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times more powerful than Earth's. This immense magnetic field traps charged particles, creating a swirling storm of radiation that surrounds the planet. These particles, mostly electrons and protons, are accelerated to nearly the speed of light, forming intense radiation belts that are thousands of times more lethal than those around Earth. The radiation is so intense that it poses a serious threat to spacecraft and would be instantly fatal to any human. Even NASA's Juno spacecraft, which orbits Jupiter, has to take special precautions to survive. Its sensitive electronics are housed in a titanium vault to shield them from the relentless bombardment of high-energy particles. Without this protection, the spacecraft would be fried in no time. But what makes Jupiter's magnetosphere truly fascinating is its sheer scale. It's so large that if it were visible to the naked eye, it would appear several times bigger than the full moon in our night sky. This magnetic bubble extends millions of miles into space, even reaching beyond the orbit of Jupiter's moon Europa. The source of this magnetic field lies deep within Jupiter's interior. Unlike Earth, which generates its magnetic field from a molten iron core, Jupiter's field is thought to arise from metallic hydrogen, a bizarre form of hydrogen that exists under extreme pressure. This swirling, electrically conductive material acts like a giant dynamo, creating the planet's colossal magnetic field. Jupiter's magnetosphere doesn't just trap radiation, it also interacts with the planet's moons. Io, one of Jupiter's most volcanic moons, spews out sulfur dioxide, which gets ionized and caught in the magnetic field. This creates a donut-shaped ring of charged particles around Jupiter, adding to the already intense radiation environment. As we move forward, we'll explore another extreme environment in our solar system, Neptune and Uranus, where the pressure and temperature conditions are so extreme that they might rain diamonds. But for now, Jupiter's magnetosphere stands as a testament to the raw, untamed power of our solar system, a place where nature's forces are on full display, creating a zone of danger and wonder unlike any other. Now, let's journey from the chaotic radiation storms of Jupiter to the icy realms of Neptune and Uranus, where the conditions are so extreme that they might just rain diamonds. Yes, you heard that right, diamonds. These distant ice giants, often overshadowed by their larger gas giant siblings, hold secrets that are as dazzling as they are mysterious. Deep within the atmospheres of Neptune and Uranus, the pressure and temperature conditions are unlike anything we experience on Earth. Here, the crushing pressure can reach millions of times that of our planet's surface, and temperatures can soar to thousands of degrees. Under these extreme conditions, something extraordinary happens to carbon, the same element that forms the graphite in your pencil and the diamonds in your jewelry. Scientists believe that the intense pressure and heat cause methane, a molecule made of carbon and hydrogen, to break apart. The carbon atoms, now free from their hydrogen bonds, are compressed so tightly that they crystallize into diamonds. These diamonds, heavier than the surrounding material, begin to sink deeper into the planet's interior, creating what researchers call diamond rain. Imagine that a shower of diamonds falling through the dense, slushy atmospheres of these distant worlds. While we can't see this phenomenon directly, laboratory experiments have recreated the extreme conditions of Neptune and Uranus, providing strong evidence that diamond rain is not just science fiction but a real possibility. What's even more fascinating is that this process might not be unique to Neptune and Uranus. Similar conditions could exist on other ice giants or even exoplanets far beyond our solar system. The idea of diamond rain opens up a whole new way of thinking about the chemistry and geology of these distant worlds, showing us just how diverse and surprising the universe can be. As we continue our exploration of the universe's most extreme environments, we'll next turn our attention to Io, one of Jupiter's moons, where rivers of molten lava flow across its surface. But for now, let's marvel at the thought of diamonds raining down on Neptune and Uranus, a reminder that even in the coldest, most distant corners of space, nature finds ways to dazzle us with its brilliance. Now, shifting our gaze from the diamond-studded skies of Neptune and Uranus, we venture closer to home, to one of Jupiter's most fiery and dramatic moons, Io. This small but mighty moon holds the title of the most volcanically active body in the entire solar system, a place where the ground itself seems to breathe fire. Io's surface is a chaotic landscape, dotted with hundreds of active volcanoes that spew molten lava high into its thin atmosphere. These eruptions are so powerful that they can create lava fountains reaching heights of hundreds of kilometers, painting the moon's surface with rivers of molten rock. Imagine standing on Io. Everywhere you look, the ground glows with the heat of flowing lava, and the horizon is lit by the constant glow of volcanic eruptions. What makes Io so incredibly active? The answer lies in its relationship with Jupiter. Io is caught in a gravitational tug of war between Jupiter and its neighboring moons, Europa and Ganymede. This constant pulling and stretching generates immense heat within Io's interior, melting its rocky core and fueling its volcanic activity. It's like a cosmic pressure cooker, with Io's surface constantly reshaping itself under the strain. One of the most striking features of Io is its lava lakes, vast pools of molten rock that can stretch for kilometers across. These lakes are not like anything on Earth. They are so hot and fluid that they behave almost like water, with waves and currents rippling across their surfaces. Some of these lakes even have islands of solid rock floating on them, slowly drifting as the lava flows beneath. But Io's volcanic activity isn't just a spectacle, it also has a profound impact on its environment. The constant eruptions release sulfur dioxide and other gases, creating a thin, toxic atmosphere. This atmosphere is constantly being stripped away by Jupiter's powerful magnetic field, only to be replenished by the next eruption. It's a cycle of destruction and renewal that has been ongoing for billions of years. As we marvel at Io's fiery beauty, it's worth noting that this moon is a reminder of how dynamic and ever-changing our solar system truly is. From diamond rain to lava lakes, the universe never ceases to amaze us with its extremes. Next, we'll turn our attention to another of Saturn's intriguing moons, Titan, where methane takes the place of water, creating lakes and rivers of an entirely different kind. But for now, let's take a moment to appreciate the raw, untamed power of Io, a world where fire reigns supreme. Now, let's journey from the fiery chaos of Io to the icy, otherworldly landscapes of Titan, Saturn's largest moon. Titan is a world unlike any other in our solar system, shrouded in a thick, hazy atmosphere and dotted with lakes and rivers, but not of water. Here, liquid methane and ethane take center stage, creating a surreal environment that feels both alien and strangely familiar. Titan's surface is a frigid wonderland, with temperatures plunging to around -290 degrees Fahrenheit. At these extreme colds, water is as hard as rock, but methane flows freely, carving channels and pooling into vast lakes. Some of these lakes are so large they rival the Great Lakes on Earth, with waves rippling across their surfaces under Titan's orange-hued skies. What makes Titan truly fascinating is its atmosphere, the only moon in the solar system with a dense, nitrogen-rich envelope. This thick haze obscures the surface from view, but spacecraft like Cassini have pierced through the veil, revealing a landscape shaped by methane rain, rivers, and even methane-based weather systems. Imagine standing on Titan, watching methane clouds drift overhead, and feeling the occasional drizzle of liquid methane, a world where the familiar cycle of evaporation and precipitation happens, but with a twist. But Titan isn't just a spectacle of hydrocarbons, it's also a prime candidate in the search for extraterrestrial life. Beneath its icy crust lies a subsurface ocean of liquid water, and scientists speculate that this hidden ocean could harbor microbial life. On the surface, the complex chemistry of methane and ethane could potentially support exotic life forms adapted to these extreme conditions. While we haven't found definitive proof yet, Titan's unique environment offers a tantalizing glimpse into the possibilities of life beyond Earth. As we explore Titan's methane lakes and rivers, we're reminded of the incredible diversity of worlds in our solar system. From the fiery volcanoes of Io to the icy hydrocarbon seas of Titan, each moon and planet tells a story of extremes. Next, we'll turn our attention to the Sun, where solar flares unleash unimaginable energy, shaping the very fabric of space weather. But for now, let's take a moment to marvel at Titan, a world where methane reigns and the search for life takes on a whole new meaning. Now, let's shift our gaze from the icy methane lakes of Titan to the blazing heart of our solar system, the Sun. This colossal ball of plasma not only sustains life on Earth, but also unleashes some of the most violent and energetic phenomena in the universe. Among these are solar flares, sudden bursts of radiation that can release as much energy as 1 billion hydrogen bombs in just a matter of minutes. Solar flares occur when magnetic energy built up in the Sun's atmosphere is suddenly released, sending a torrent of charged particles and radiation hurtling into space. These eruptions are so powerful that they can disrupt satellites, interfere with communication systems, and even knock out power grids on Earth. Imagine the chaos of a massive solar flare striking our planet, GPS systems failing, radio signals dropping, and entire regions plunged into darkness. But solar flares aren't just destructive, they also play a crucial role in shaping space weather. This invisible force governs the conditions in the space surrounding Earth, influencing everything from the auroras that light up our polar skies to the safety of astronauts in orbit. When a solar flare erupts, it sends shockwaves through the solar system, creating a cascade of effects that ripple across millions of miles. One of the most stunning consequences of solar flares is the aurora borealis, or northern lights. When charged particles from a flare collide with Earth's magnetic field, they create dazzling displays of light in the upper atmosphere. These shimmering curtains of green, pink, and purple are a reminder of the Sun's immense power and its profound impact on our planet. Yet, for all their beauty, solar flares also pose significant risks. Astronauts aboard the International Space Station must take shelter during intense solar activity to avoid harmful radiation. Even spacecraft and satellites are vulnerable, as the high-energy particles can damage sensitive electronics and shorten their operational lifespans. As we marvel at the Sun's fiery outbursts, we're reminded of the delicate balance that allows life to thrive on Earth. Our planet's magnetic field and atmosphere act as a shield, protecting us from the worst effects of solar flares. But as our reliance on technology grows, so does our vulnerability to these cosmic storms. Next, we'll venture into the void of space itself, where the absence of pressure and temperature creates an environment unlike any other. But for now, let's take a moment to appreciate the Sun's dual nature, both a life-giving force and a source of unimaginable power. Solar flares are a testament to the dynamic and ever-changing nature of our universe, a reminder that even the most familiar celestial bodies can hold surprises beyond our wildest imagination. Now, let's step away from the Sun's fiery outbursts and into the vast, silent expanse of space itself, a place where the rules of our everyday world no longer apply. Space is not just empty, it's a vacuum, an environment so extreme that it defies our basic understanding of how matter and energy behave. In the vacuum of space, there's no air, no pressure, and no temperature as we know it. Instead, it's a realm of extremes where the absence of atmosphere can cause liquids to boil instantly or freeze solid in a matter of seconds. Imagine a cup of water floating in space. Without the pressure of Earth's atmosphere, the water would begin to boil immediately, even if it's at a temperature that would feel icy cold to us. At the same time, any heat in the water would radiate away into the void, causing it to freeze just as quickly. This bizarre interplay of boiling and freezing is just one example of how space challenges our intuition. But how do astronauts survive in such a hostile environment? The answer lies in the incredible technology of spacesuits and spacecraft. Spacesuits are essentially miniature spacecraft designed to maintain a stable pressure and temperature around the astronaut's body. They provide oxygen to breathe, remove carbon dioxide, and protect against the vacuum's deadly effects. Without these suits, the human body would face catastrophic consequences: blood boiling, lungs collapsing, and tissues swelling due to the lack of pressure. Spacecraft, too, are marvels of engineering, creating a bubble of Earth-like conditions in the void. They regulate temperature, provide breathable air, and shield astronauts from the vacuum's dangers. Even so, living in space is far from easy. astronauts must constantly monitor their environment, ensuring that their life support systems are functioning perfectly. A single leak or malfunction could spell disaster in the unforgiving vacuum of space. The vacuum of space also poses unique challenges for equipment and experiments. Without air to conduct heat, spacecraft must rely on radiators to dissipate excess warmth. Tools and materials behave differently. Too, lubricants evaporate, metals can weld together without oxygen, and even the simplest tasks require careful planning. Yet, despite its harshness, the vacuum of space is also a place of incredible opportunity. It's a pristine environment for scientific research, free from the interference of Earth's atmosphere. Telescopes like the Hubble Space Telescope have used the vacuum to peer deeper into the cosmos than ever before, revealing galaxies billions of light years away. As we reflect on the vacuum of space, we're reminded of the ingenuity and resilience required to explore such an extreme environment. It's a testament to human curiosity and determination, pushing the boundaries of what's possible. Next, we'll turn our attention to the stars that defy the norms of the cosmos, hypervelocity stars, racing through the universe at unimaginable speeds. But for now, let's marvel at the vacuum of space, a silent, empty frontier that continues to inspire and challenge us. Now, let's shift our gaze from the silent vacuum of space to the stars that race across the cosmos at breathtaking speeds, hypervelocity stars. These stellar speedsters are unlike anything you've ever imagined, hurtling through the universe at millions of miles per hour, so fast that they can escape the gravitational pull of their own galaxies. But how do stars reach such incredible velocities? The answer lies in some of the most extreme events in the universe. Hypervelocity stars are often born from violent encounters with supermassive black holes. Imagine a star wandering too close to the edge of a black hole's immense gravitational field. Instead of being swallowed whole, it can be slingshotted away at astonishing speeds like a cosmic catapult. This process, known as the Hill's mechanism, can fling stars out of their galaxies entirely, sending them on a one-way journey into intergalactic space. But black holes aren't the only culprits. Supernova explosions can also launch stars into hypervelocity motion. When a massive star explodes, the sheer force of the blast can propel its companion star outward at incredible speeds like a cosmic pinball. These runaway stars then travel through the void, leaving their home galaxies far behind. What makes hypervelocity stars so fascinating is not just their speed but their rarity. Only a handful have been discovered so far, each one a cosmic anomaly. Scientists study these stars to learn more about the forces that shape our universe, from the behavior of black holes to the dynamics of galaxy formation. One of the most famous hypervelocity stars is known as S5 HVS1, discovered racing through the Milky Way at over 1 million miles per hour. This star is believed to have been ejected from the center of our galaxy by the supermassive black hole Sagittarius A star, offering a glimpse into the extreme processes at work in the heart of the Milky Way. As we marvel at these stellar speedsters, we're reminded of the universe's capacity for both destruction and creation. Hypervelocity stars are a testament to the incredible forces at play in the cosmos, forces that can fling stars across the void and reshape the fabric of space itself. Next, we'll dive into the densest objects in the universe, neutron stars, where a single teaspoon of material weighs billions of tons. But for now, let's take a moment to appreciate the sheer audacity of hypervelocity stars, racing through the cosmos like cosmic outlaws forever on the run. Now, let's turn our attention to one of the most mind-bending objects in the universe, neutron stars. These cosmic powerhouses are the remnants of massive stars that have exploded in supernova, leaving behind cores so dense that they defy imagination. To put it into perspective, imagine taking a sugar cube-sized piece of a neutron star. That tiny fragment would weigh billions of tons, yes, billions. It's a staggering thought, isn't it? Neutron stars are born from the collapse of stars much larger than our Sun. When these stars exhaust their fuel, they explode in a supernova and their cores collapse under their own gravity. What's left is a neutron star, a city-sized object packing the mass of a star into a sphere only about 12 miles across. The density is so extreme that protons and electrons are crushed together, forming neutrons, hence the name. But the density isn't the only jaw-dropping feature of neutron stars. Their magnetic fields are equally extreme, trillions of times stronger than Earth's. These magnetic fields are so powerful that they can distort the very fabric of space-time around them. And if that weren't enough, neutron stars also have an immense gravitational pull. If you were to stand on the surface of a neutron star, which, by the way, is impossible because you'd be instantly crushed, you'd experience a gravitational force billions of times stronger than what we feel on Earth. One of the most fascinating aspects of neutron stars is their crust. This outer layer, only about half a mile thick, is incredibly rigid and solid despite the unimaginable pressures beneath it. The crust is made up of atomic nuclei arranged in a lattice with a sea of free-flowing neutrons beneath. Occasionally, the crust can crack under the immense stress, causing starquakes, cosmic tremors that release bursts of energy detectable across the galaxy. Neutron stars are also known for their precision. Some of them, called pulsars, spin at incredible speeds, emitting beams of radiation that sweep across the cosmos like cosmic lighthouses. These beams are so regular that pulsars are often used as natural clocks, helping scientists test theories of gravity and space-time. As we explore the extreme environments of neutron stars, we're reminded of the universe's ability to push the boundaries of what we thought was possible. These objects are not just remnants of stellar explosions, they're laboratories for some of the most extreme physics in the cosmos. Next, we'll venture into the realm of the universe's most energetic explosions, gamma-ray bursts. But for now, let's take a moment to marvel at the sheer density and power of neutron stars, where a teaspoon of material holds the weight of mountains and the secrets of the universe itself. Now, let's shift our gaze to one of the most explosive phenomena in the cosmos, gamma-ray bursts. These are the universe's ultimate fireworks, releasing more energy in mere seconds than our Sun will emit over its entire 10 billion-year lifespan. To put that into perspective, imagine the Sun's total energy output compressed into a single, blinding flash. That's the raw power of a gamma-ray burst. Gamma-ray bursts are thought to occur during some of the most cataclysmic events in the universe, such as the collapse of massive stars into black holes or the collision of neutron stars. When these events happen, they unleash jets of energy that travel at nearly the speed of light, emitting gamma rays, the most energetic form of light. These bursts are so intense that they can be detected from billions of light years away, making them some of the most distant and ancient events we've ever observed. What makes gamma-ray bursts even more fascinating is their unpredictability. They can last anywhere from a fraction of a second to several minutes, and they appear randomly across the sky. Scientists have no way of predicting when or where the next one will occur, which adds to their mystery. When a gamma-ray burst is detected, it's a race against time for astronomers to point their telescopes in its direction, hoping to catch a glimpse of the afterglow, a fading echo of light that reveals clues about the burst's origin. The energy released during a gamma-ray burst is so immense that, if one were to occur within our galaxy, it could have devastating effects on Earth. The intense radiation could strip away our ozone layer, exposing the planet to harmful ultraviolet rays from the Sun. Fortunately, gamma-ray bursts are rare, and the likelihood of one happening close enough to affect us is extremely low. Despite their destructive potential, gamma-ray bursts are invaluable to scientists. They serve as cosmic beacons, allowing us to probe the distant reaches of the universe and study the conditions that existed shortly after the Big Bang. By analyzing the light from these bursts, researchers can learn about the early universe, the formation of galaxies, and the behavior of matter under extreme conditions. As we marvel at the sheer power of gamma-ray bursts, we're reminded of the universe's capacity for both creation and destruction. These fleeting flashes of energy are not just cosmic curiosities. They're windows into the most extreme environments and events in the cosmos. Next, we'll journey to the icy fringes of our solar system, where the Oort cloud holds secrets of the universe's earliest days. But for now, let's take a moment to reflect on the awe-inspiring energy of gamma-ray bursts, where the universe's most violent moments illuminate its deepest mysteries. Now, let's venture to the outermost reaches of our solar system, where the Oort cloud lies in quiet obscurity. This vast, icy realm is a cosmic treasure trove, home to trillions of frozen bodies that have remained largely unchanged since the dawn of our solar system. Stretching nearly 1 light-year from the Sun, the Oort cloud is so distant that it marks the boundary where the Sun's gravitational influence begins to wane, giving way to the interstellar void. The Oort cloud is often described as a spherical shell of icy debris, a relic from the formation of the solar system over 4.5 billion years ago. These icy remnants are thought to be the building blocks left over after the planets took shape, preserved in the deep freeze of space. While we've never directly observed the Oort cloud, its objects are too faint and far away. Its existence is inferred from the behavior of long-period comets. These comets, which take thousands or even millions of years to orbit the Sun, are believed to originate from this distant reservoir. What makes the Oort cloud truly fascinating is its role as a cosmic time capsule. The icy bodies within it have remained largely untouched since the solar system's infancy, offering scientists a glimpse into the conditions that existed when the planets were forming. When a comet is nudged out of the Oort cloud and begins its long journey toward the Sun, it carries with it clues about the early chemistry and composition of our solar system. As these comets approach the inner solar system, they heat up, releasing gases and dust that form their iconic tails. This process allows astronomers to study the primordial materials that once swirled around the young Sun. The Oort cloud also serves as a reminder of the solar system's dynamic nature. Gravitational interactions with passing stars or the Milky Way's tidal forces can dislodge these icy bodies, sending them hurtling toward the inner solar system. Some of these comets may collide with planets, delivering water and organic molecules that could have played a role in the emergence of life on Earth. Others might be ejected into interstellar space, becoming rogue comets that wander the galaxy. Despite its immense size and significance, the Oort cloud remains one of the least understood regions of our solar system. Its distance makes it a challenging target for exploration, but future missions and advanced telescopes may one day reveal its secrets. For now, it stands as a testament to the solar system's enduring mysteries, a frozen frontier that continues to captivate our imagination. As we reflect on the Oort cloud's icy remnants, we're reminded of the delicate balance that shapes our cosmic neighborhood. Next, we'll turn our attention to the enigmatic rogue planets, worlds that drift through the darkness of space without a star to call home. But for now, let's marvel at the Oort cloud, a distant and ancient archive that holds the story of our solar system's beginnings. Now, let's shift our gaze to the shadowy wanderers of the cosmos' rogue planets. Unlike the planets we're familiar with, these mysterious worlds don't orbit a star. Instead, they drift freely through the vast emptiness of space, untethered and alone. Imagine a planet, cold and dark, moving silently through the interstellar void, where temperatures can plunge to hundreds of degrees below freezing. These rogue planets are the ultimate cosmic nomads, enduring some of the most extreme conditions imaginable. Rogue planets are thought to form in one of two ways. Some may have been born in the chaos of a young star system, only to be flung out into space by gravitational interactions with larger planets. Others might have formed on their own, collapsing directly from clouds of gas and dust without ever becoming part of a star system. Regardless of their origins, these planets are left to wander the galaxy, far from the warmth and light of a star. Despite their harsh environments, rogue planets might not be as lifeless as they seem. Scientists speculate that some of these worlds could harbor subsurface oceans, kept liquid by the heat generated from radioactive decay or tidal forces. If such oceans exist, they could potentially support microbial life, much like the icy moons of Jupiter and Saturn. The idea of life thriving in the darkness of space, hidden beneath layers of ice, challenges our understanding of where life can exist. Rogue planets also raise intriguing questions about the nature of planetary systems. How common are these free-floating worlds? Some estimates suggest there could be billions of them in our galaxy alone, outnumbering stars. Yet, because they emit no light and are incredibly difficult to detect, they remain largely hidden from our view. Advances in technology, such as microlensing surveys, have begun to reveal their presence, offering glimpses into this shadowy population. What's even more fascinating is the possibility that rogue planets could serve as stepping stones for life across the galaxy. If a rogue planet were to pass close to a star system, it might capture a moon or even be pulled into orbit, potentially bringing life with it. This idea opens up a tantalizing scenario where life could spread from one star system to another, carried by these wandering worlds. As we ponder the existence of rogue planets, we're reminded of the vast diversity of worlds in the universe. These lonely travelers challenge our assumptions and expand our imagination, showing us that even in the coldest, darkest corners of space, there may still be the potential for life. Next, we'll journey to the heart of a quasar, where the brightest objects in the universe reveal the incredible power of supermassive black holes. But for now, let's marvel at the enigmatic rogue planets, the silent wanderers of the cosmic expanse. Now, let's turn our attention to one of the most dazzling phenomena in the cosmos: quasars. These celestial powerhouses are the brightest objects in the universe, outshining entire galaxies with their incredible luminosity. At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. But what makes quasars truly extraordinary is the way they consume matter. As gas, dust, and even stars spiral into the black hole, they form a swirling disk of superheated material. This disk glows so intensely that it can be seen across billions of light years, lighting up the darkest corners of the universe. Quasars are not just bright, they are also incredibly energetic. The process of matter falling into the black hole releases staggering amounts of energy, often in the form of powerful jets that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for thousands of light years, carving through space and influencing the surrounding galaxies. In fact, quasars are so energetic that they can outshine all the stars in their host galaxies combined, making them visible even from the farthest reaches of the observable universe. But quasars are more than just cosmic light shows. They play a crucial role in the evolution of galaxies. The intense radiation and powerful jets emitted by quasars can heat up and push away gas in their host galaxies, regulating star formation and shaping the structure of the galaxy itself. In some cases, quasars may even trigger the birth of new stars by compressing gas clouds as their jets blast through the galaxy. This delicate balance between destruction and creation highlights the profound influence quasars have on their cosmic surroundings. Interestingly, quasars are also time capsules. Because light takes time to travel across the universe, the light we see from distant quasars today actually left them billions of years ago. By studying quasars, astronomers can peer back in time to the early universe, when galaxies were still forming and the cosmos was a much more chaotic place. Quasars provide a unique window into this ancient era, helping us understand how galaxies and supermassive black holes evolved over billions of years. As we marvel at the brilliance of quasars, we're reminded of the incredible forces at work in the universe. These luminous cores, powered by the insatiable appetite of supermassive black holes, are a testament to the dynamic and ever-changing nature of the cosmos. Next, we'll explore the faint glow of the Big Bang itself, the cosmic microwave background, and how it helps us unravel the origins of the universe. But for now, let's bask in the awe-inspiring light of quasars, the brightest beacons in the cosmic darkness. Now let's journey back to the very beginning of everything, the Big Bang. Imagine the universe as a newborn just moments after its birth, filled with a searing, dense fog of energy and particles. As the universe expanded and cooled, this primordial glow began to fade, leaving behind a faint whisper of light that still permeates the cosmos today. This is the cosmic microwave background, or CMB, the oldest light in the universe and a direct snapshot of its infancy. The CMB is like a cosmic fingerprint imprinted on the sky roughly 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that light couldn't travel freely. It was constantly scattered by the soup of charged particles. But as the universe cooled, electrons and protons combined to form neutral atoms, allowing light to finally break free. This first light, now stretched by the expansion of the universe over billions of years, reaches us as microwave radiation, a faint glow that fills the entire sky. What makes the CMB so extraordinary is its uniformity. No matter where you look in the sky, the temperature of this ancient light is nearly the same, hovering just above absolute zero. But within this uniformity lie tiny fluctuations, minute variations in temperature that hold the key to understanding the universe's structure. These tiny ripples are the seeds of all cosmic structures we see today: galaxies, clusters of galaxies, and even the vast cosmic web that connects them. Without these fluctuations, the universe would be a featureless void, devoid of stars, planets, or life. The discovery of the CMB in 1965 was a monumental moment in cosmology. It provided the first solid evidence for the Big Bang theory, confirming that the universe had a hot, dense beginning. Since then, detailed observations of the CMB, such as those made by the Planck satellite, have allowed scientists to measure the universe's age, composition, and expansion rate with incredible precision. We now know that the universe is approximately 13.8 billion years old, and that it is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. But the CMB isn't just a relic of the past, it's also a window into the future. By studying its patterns, scientists can test theories about the universe's ultimate fate. Will it continue expanding forever, or will it eventually collapse back in on itself? The answers may lie hidden in the subtle details of this ancient light. As we ponder the cosmic microwave background, we're reminded of how far we've come in understanding the universe. This faint glow, a remnant of the Big Bang, connects us to the very origins of everything. It's a humbling reminder that the universe has a story to tell, and we're just beginning to read its pages. Next, we'll dive into the mysterious world of magnetars, neutron stars with magnetic fields so powerful they can warp space itself. But for now, let's take a moment to appreciate the CMB, the oldest light in the universe and a beacon from the dawn of time. Now, let's turn our attention to one of the most extreme and mysterious objects in the universe: magnetars. These are not your average neutron stars. Imagine a star so dense that a single teaspoon of its material would weigh billions of tons. Now, take that density and combine it with a magnetic field trillions of times stronger than Earth. That's a magnetar, a cosmic powerhouse that defies imagination. Magnetars are born from the explosive deaths of massive stars, collapsing into neutron stars with a twist. Their magnetic fields are so intense that they can distort the very fabric of space-time. To put this into perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would erase the data on every credit card on our planet. That's how powerful these forces are. But what makes magnetars truly fascinating is their ability to unleash sudden, violent bursts of energy. These outbursts, known as starquakes, occur when the magnetar's crust cracks under the strain of its own magnetic field. When this happens, the star releases an enormous amount of energy in the form of gamma rays and X-rays, lighting up the cosmos like a cosmic flare. In fact, some of the brightest flashes of gamma rays ever detected have come from magnetars. The impact of these magnetic fields doesn't stop at energy bursts. Magnetars can also create ripples in space-time itself, a phenomenon predicted by Einstein's theory of general relativity. These ripples, known as gravitational waves, are like cosmic echoes that travel across the universe, carrying information about the events that created them. While we've detected gravitational waves from black hole mergers, magnetars offer another exciting avenue for studying these elusive signals. Despite their destructive potential, magnetars also provide a unique laboratory for testing the laws of physics under extreme conditions. Scientists study them to better understand how matter behaves under such intense magnetic fields and to explore the limits of our current theories. What happens to atoms in these environments? How does space-time react to such forces? These are questions that magnetars help us answer. As we marvel at the sheer power of magnetars, we're reminded of how much we still have to learn about the universe. These cosmic giants challenge our understanding of physics and push the boundaries of what we thought was possible. Next, we'll explore another extreme environment, an exoplanet where molten glass rains sideways at unimaginable speeds. But for now, let's take a moment to appreciate the awe-inspiring might of magnetars, the universe's ultimate magnetic marvels. Now, let's shift our gaze to a world that feels like it's been plucked straight out of a science fiction novel, HD 189733b. This exoplanet, located about 63 light-years from Earth, is a place where the weather is anything but ordinary. Imagine winds so fierce they could strip the paint off a spaceship, reaching speeds of 5,400 miles per hour or 8,700 kilometers per hour. But that's not even the most bizarre part. On HD 189733b, it rains molten glass, and not just any rain. This glass falls sideways, driven by those unimaginably powerful winds. The planet's atmosphere is a swirling mix of silicate particles, which, under the extreme heat, condense into tiny droplets of molten glass. These droplets are then whipped around by the supersonic winds, creating a sideways rainstorm that would be both terrifying and mesmerizing to witness. The temperature on this exoplanet is scorching, reaching up to 1,700 degrees Celsius or 3,092 degrees Fahrenheit. That's hot enough to melt metal, let alone glass. What makes HD 189733b even more fascinating is its deep blue color, reminiscent of Earth's oceans when viewed from space. But don't let that serene appearance fool you. This blue hue comes not from water, but from the scattering of light through the silicate-rich atmosphere. It's a reminder that beauty in the cosmos often comes with a side of danger. Scientists study planets like HD 189733b to better understand the diversity of exoplanetary atmospheres and the extreme conditions that can exist beyond our solar system. These findings help us refine our models of planetary formation and climate, offering clues about how different factors, like a star's proximity or a planet's composition, can create such wildly different environments. As we ponder the sideways glass rain and supersonic winds of HD 189733b, we're reminded of just how strange and varied the universe can be. This exoplanet challenges our imagination and expands our understanding of what's possible in the cosmos. Next, we'll delve into the invisible force that shapes galaxies and holds the universe together, dark matter. But for now, let's take a moment to marvel at the sheer audacity of a world where the sky rains molten glass. Now, let's turn our attention to one of the greatest mysteries in the cosmos: dark matter. This invisible substance makes up a staggering 85% of the universe's total mass, yet it remains completely undetectable by conventional means. Unlike stars, planets, or even gas clouds, dark matter doesn't emit, absorb, or reflect light. It's as if the universe is filled with a ghostly presence, silently shaping everything around us. So, how do we know dark matter exists if we can't see it? The answer lies in its gravitational effects. Scientists first noticed something unusual when observing the way galaxies rotate. The outer regions of galaxies were moving far too quickly to be explained by the visible matter alone. This discrepancy led to the conclusion that there must be some unseen mass exerting a gravitational pull, holding these galaxies together. Without dark matter, galaxies would simply fly apart, but dark matter's influence doesn't stop at galaxies. It plays a crucial role in the large-scale structure of the universe. Think of it as the cosmic scaffolding that holds everything in place. When the universe was young, dark matter's gravitational pull caused ordinary matter to clump together, forming the first galaxies and galaxy clusters. Even today, it continues to shape the distribution of galaxies across the vast expanse of space. Despite its importance, dark matter remains one of the most elusive subjects in modern science. Researchers have proposed various theories about what it might be made of, from weakly interacting massive particles, or WIMP, to actions hypothetical particles that could solve multiple cosmic puzzles. Yet, despite decades of searching, no direct detection of dark matter has been confirmed. It's a reminder that, even with all our advancements, the universe still holds secrets we've only begun to uncover. As we ponder the invisible force that shapes the cosmos, we're reminded of how much there is still to learn. Dark matter challenges our understanding of physics and the very fabric of reality. It's a testament to the universe's complexity and the endless possibilities that await discovery. Next, we'll explore another cosmic enigma, the Great Attractor, a mysterious gravitational anomaly pulling galaxies toward it. But for now, let's marvel at the invisible hand that holds the universe together, shaping the stars, galaxies, and even our own existence. Now, let's journey deeper into the cosmos to uncover another fascinating mystery, the Great Attractor. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This gravitational anomaly, located roughly 250 million light-years away, has puzzled scientists for decades. But here's the twist: we can't see it directly. The Great Attractor lies hidden behind the dense plane of the Milky Way, obscured by stars, gas, and dust. It's like trying to find a hidden treasure buried under layers of cosmic fog. So, how did we even discover this invisible force? It all started with observations of galaxy movements. In the 1970s, astronomers noticed something unusual. Galaxies, including ours, were all moving toward a specific region of space at speeds of over 600 kilometers per second. This motion couldn't be explained by the visible matter in the universe alone. Something massive and unseen was tugging at these galaxies, and that something became known as the Great Attractor. But studying it is no easy task. The Milky Way's galactic plane blocks our view, making it nearly impossible to observe the Great Attractor directly with optical telescopes. Instead, scientists rely on other wavelengths, like radio and infrared, to peer through the cosmic veil. These observations have revealed that the Great Attractor isn't just a single object, but a massive concentration of galaxies and dark matter, forming a supercluster known as the Laniakea supercluster. This supercluster spans over 500 million light-years and contains tens of thousands of galaxies, all bound together by gravity. The Great Attractor's pull is so strong that it's reshaping the large-scale structure of the universe. It's not just our galaxy that's being drawn in. Countless others are on the same cosmic journey. But here's the kicker: the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster, the most massive concentration of galaxies in the observable universe. It's a cosmic tug of war on an unimaginable scale. Despite the challenges, studying the Great Attractor offers valuable insights into the universe's structure and evolution. It reminds us that even in the vastness of space, everything is connected by gravity, weaving a complex web of motion and interaction. As we continue to unravel its secrets, the Great Attractor stands as a testament to the universe's endless mysteries and the relentless curiosity that drives us to explore them. Next, we'll turn our attention to the precision of pulsars, the cosmic lighthouses that guide us through the depths of space. But for now, let's marvel at the unseen force that's shaping the destiny of galaxies, including our own. Now, let's shift our gaze to one of the most precise phenomena in the universe: pulsars. Imagine a star so dense that a teaspoon of its material would weigh billions of tons, spinning hundreds of times per second and emitting beams of radiation like a cosmic lighthouse. These rapidly spinning neutron stars, born from the explosive deaths of massive stars, are not just remnants of stellar cataclysms, they're also some of the most accurate timekeepers in the cosmos. Pulsars get their name from the way they pulse or blink as they rotate. This happens because their intense magnetic fields channel radiation into narrow beams that sweep across space like the beam of a lighthouse. Every time one of these beams points toward Earth, we detect a pulse of light or radio waves. What's truly astonishing is the precision of these pulses. Some pulsars rotate with such regularity that their pulses can be predicted to within a fraction of a millisecond over years, even decades. It's like having a cosmic clock that never loses a second. This incredible precision makes pulsars invaluable tools for astronomers. For example, the first exoplanets ever discovered were found orbiting a pulsar, thanks to the slight variations in the timing of its pulses caused by the gravitational tug of the planets. Pulsars have also been used to test Einstein's theory of general relativity. In one famous experiment, astronomers observed a pair of pulsars orbiting each other and found that their orbits were decaying exactly as predicted by Einstein's equations, providing some of the strongest evidence for the theory. But pulsars aren't just scientific tools, they're also cosmic survivors. These neutron stars endure some of the most extreme conditions in the universe. Their surfaces are so dense that a single cubic centimeter of material would weigh as much as a mountain. Their magnetic fields are trillions of times stronger than Earth's, capable of ripping apart atoms. And yet, despite these extreme conditions, pulsars continue to spin with unerring precision, lighting up the universe with their rhythmic pulses. As we marvel at the precision of pulsars, we're reminded of the universe's ability to create order out of chaos. These cosmic lighthouses not only guide us through the depths of space, but also offer a glimpse into the fundamental laws that govern the cosmos. Next, we'll explore the hypergiant stars, the largest and most luminous stars in the universe, whose brilliance outshines even the most dazzling cosmic phenomena. But for now, let's take a moment to appreciate the pulsars, nature's perfect timekeepers spinning tirelessly in the vast expanse of space. Now, let's turn our attention to the titans of the cosmos, hypergiant stars. These colossal stars are the largest and most luminous objects in the universe, dwarfing even the most massive stars we've encountered so far. Imagine a star so bright that it outshines our sun by billions of times, radiating energy at a rate that defies comprehension. Hypergiants are the true heavyweights of the stellar world, and their existence pushes the boundaries of what we thought was possible in the universe. Hypergiant stars are not just big, they are unimaginably massive. Some of these stars can be hundreds of times larger than the Sun, with diameters stretching across billions of kilometers. To put that into perspective, if you placed a hypergiant star in the center of our solar system, its outer layers could extend beyond the orbit of Jupiter. But their size is only part of what makes them extraordinary. These stars are also incredibly luminous, emitting energy at a staggering rate. In fact, a single hypergiant can shine with the brightness of millions of suns combined, lighting up entire galaxies with their brilliance. However, such extreme power comes at a cost. Hypergiant stars live fast and die young. Unlike the Sun, which will burn steadily for billions of years, hypergiants have lifespans measured in mere millions of years, a cosmic blink of an eye. Their immense size and luminosity mean they burn through their fuel at an astonishing rate, leading to explosive and dramatic ends. When a hypergiant star exhausts its fuel, it doesn't go quietly. Instead, it often ends its life in a spectacular supernova, one of the most energetic events in the universe. These explosions can outshine entire galaxies and leave behind remnants like neutron stars or black holes, shaping the cosmos in their wake. One of the most famous hypergiant stars is Eta Carinae, located in the Carina constellation. This star is so massive and unstable that it has already undergone several violent eruptions, ejecting vast amounts of material into space. Astronomers believe Eta Carinae is on the brink of a catastrophic explosion, and when it finally goes supernova, it could become one of the brightest objects in the night sky, visible even during the day. Hypergiant stars remind us of the universe's capacity for extremes. They are both creators and destroyers, forging the elements that make up planets, stars, and even life itself, while also unleashing unimaginable energy that reshapes the cosmos. As we marvel at their brilliance, we're reminded of the delicate balance that governs the lives of stars, a balance that, for hypergiants, tips toward the spectacular and the fleeting. Next, we'll venture into the cosmic voids, the vast, empty regions of space where galaxies are scarce, and explore the mysteries they hold. But for now, let's take a moment to appreciate the hypergiant stars, the luminous giants that light up the universe, even if only for a short while. Now, let's shift our gaze from the luminous giants of the cosmos to the eerie emptiness of cosmic voids. These vast, desolate regions of space are the antithesis of the bustling galaxy clusters and hypergiant stars we've explored so far. Imagine a place so empty that it stretches for hundreds of millions of light years, with only a handful of galaxies scattered across its expanse. Cosmic voids are the universe's quiet corners, where the density of matter is so low that they feel almost like a vacuum compared to the rest of the cosmos. But don't let their emptiness fool you. Cosmic voids play a crucial role in shaping the large-scale structure of the universe. They are the negative spaces in the cosmic web, the intricate network of filaments and clusters that connect galaxies across the universe. Think of the universe as a sponge, with galaxies clustered along the sponge's strands and voids occupying the empty holes. These voids are not random. They are the result of the universe's expansion and the gravitational tug of war between matter and dark energy. Over billions of years, galaxies have been pulled toward denser regions, leaving behind these vast, empty spaces. One of the largest known voids is the Boötes void, a region spanning over 300 million light-years. To put that into perspective, if you place the Milky Way in the center of the Boötes void, the nearest galaxy would be so far away that it would feel like an island in an ocean of nothingness. Yet, even in these seemingly barren regions, there are surprises. Astronomers have discovered faint galaxies and mysterious structures within voids, hinting that these areas are not entirely devoid of activity. Cosmic voids also hold clues to some of the universe's greatest mysteries. For instance, they provide a unique environment to study dark energy, the mysterious force driving the universe's accelerated expansion. Because voids are less influenced by gravity, they expand faster than denser regions, making them ideal laboratories for understanding how dark energy shapes the cosmos. Additionally, the distribution of voids helps scientists test theories about the universe's origins and evolution, offering insights into the Big Bang and the formation of the cosmic web. While they may seem like empty, unremarkable spaces, cosmic voids are essential to the universe's grand design. They remind us that even in the vastness of space, emptiness has its purpose, shaping the structure of everything we see. As we continue our journey through the universe's most extreme environments, We'll next explore the mind-bending effects of time dilation near black holes where gravity warps time itself. But for now, let's take a moment to appreciate the cosmic voids, the silent architects of the universe's structure, quietly shaping the cosmos in ways we're only beginning to understand. Now, let's venture into one of the most mind-bending phenomena in the universe: time dilation near black holes. Imagine standing on the edge of a black hole, where the gravitational pull is so intense that it warps not just space but time itself. This is the realm where the rules of physics as we know them begin to twist and turn in ways that challenge our understanding of reality. Near a black hole, time doesn't flow at the same rate as it does here on Earth. Instead, it slows down dramatically, creating effects that seem straight out of science fiction. To understand this, let's break it down. Time dilation is a consequence of Einstein's theory of general relativity, which tells us that gravity can bend time. The stronger the gravitational field, the more time slows down. Near a black hole where gravity is at its most extreme, this effect becomes incredibly pronounced. For an observer watching from a safe distance, someone falling toward a black hole would appear to move slower and slower, almost as if they were frozen in time. But for the person falling in, time would feel normal until they reached the event horizon, the point of no return where the laws of physics as we know them break down completely. This bizarre effect isn't just theoretical. It has real-world implications for how we study black holes and the universe. For example, if you could somehow orbit a black hole and then return to Earth, you'd find that less time has passed for you than for everyone else. This means you could, in a sense, travel into the future. While this might sound like the plot of a sci-fi movie, it's grounded in the very real physics of extreme gravity. Black holes, with their immense gravitational pull, act as natural time machines, stretching and compressing time in ways that are both fascinating and terrifying. But time dilation near black holes isn't just about slowing time. It also affects light and matter in strange ways. As objects approach a black hole, their light gets stretched into longer, redder wavelengths, a phenomenon known as gravitational redshift. This means that if you were watching someone fall into a black hole, they would gradually fade from view, their light becoming dimmer and redder until it disappears entirely. It's a haunting reminder of the black hole's power to warp not just space and time, but even the light that tries to escape its grasp. As we peel back the layers of this cosmic mystery, we're left with a profound sense of awe. Black holes are more than just destructive forces. They're windows into the extreme limits of physics, where time and space are stretched to their breaking point. And as we prepare to explore our final fact, the speculative and mind-expanding concept of the multiverse, we're reminded that the universe is full of wonders that defy our imagination. But for now, let's take a moment to reflect on the incredible power of black holes, where time itself bends to the will of gravity, creating a reality that's as strange as it is beautiful. Now, let's step into the realm of the truly speculative, where the boundaries of our universe dissolve, and the concept of reality expands beyond comprehension. This brings us to our final fact, the multiverse theory. Imagine, if you will, that our universe is just one of countless others, each with its own unique set of physical laws and extreme environments. It's a mind-bending idea that challenges everything we think we know about existence. The multiverse theory suggests that our universe might be part of a vast cosmic tapestry, where multiple universes coexist, each operating under different rules. In some of these universes, the laws of physics might be so alien that stars, planets, and even life as we know it could never exist. In others, gravity might be stronger, time might flow backward, or matter might behave in ways that defy our understanding. The possibilities are as endless as they are fascinating. One of the most compelling arguments for the multiverse comes from the field of quantum mechanics. According to some interpretations, every time a quantum event occurs, like the decay of an atom or the spin of an electron, the universe splits into multiple versions, each representing a different outcome. This means that somewhere out there could be a universe where you made a different choice this morning, or where history unfolded in an entirely different way. It's a dizzying thought, but one that highlights the sheer complexity of the cosmos. Another angle comes from cosmology, particularly the idea of cosmic inflation. This theory suggests that in the moments after the Big Bang, space expanded at an incredible rate, creating pockets of space-time that could have developed into separate universes. These universes, often referred to as bubble universes, might be floating in a vast cosmic ocean, each with its own unique properties and conditions. Some might be teeming with life, while others could be barren and inhospitable. But why does the multiverse matter beyond its sheer fascination? The concept forces us to rethink our place in the grand scheme of things. If our universe is just one of many, it humbles us, reminding us that there's still so much we don't know. It also opens up new avenues for scientific exploration, challenging us to think beyond the limits of our own reality and consider the infinite possibilities that might exist beyond it. As we wrap up our journey through the universe's most extreme environments, the multiverse theory leaves us with a profound sense of wonder. It's a reminder that the cosmos is far stranger and more complex than we can imagine, filled with mysteries that push the boundaries of science and philosophy. Whether or not the multiverse exists, the idea itself inspires us to keep exploring, questioning, and dreaming about the infinite possibilities that lie beyond the stars. And with that, we conclude our cosmic adventure, but the universe's secrets are far from exhausted. What will we discover next? Only time and perhaps a few more universes will tell. And so, we've reached the end of our journey through the universe's most extreme environments, a voyage that has taken us from the scorching surface of Venus to the icy plains of Pluto, from the crushing gravity of black holes to the diamond rain of Neptune and Uranus. We've marveled at the volcanic fury of Io, the methane rivers of Titan, and the deadly radiation storms of Jupiter. We've pondered the mysteries of dark matter, the precision of pulsars, and the mind-bending possibilities of the multiverse. Each of these 25 facts has revealed a universe that is stranger, more violent, and more beautiful than we could have ever imagined. What's truly remarkable is how these extreme environments challenge our understanding of reality. They remind us that the universe is not just a collection of stars and planets, but a dynamic, ever-changing tapestry of forces and phenomena. From the smallest particles to the largest cosmic structures, every corner of the cosmos holds secrets waiting to be uncovered. Now we want to hear from you. Which of these facts left you the most amazed? Was it the idea of diamond rain, the sheer power of gamma-ray bursts, or the mind-bending concept of time dilation near black holes? Let us know in the comments below. We'd love to hear your thoughts and spark a conversation about the wonders of the universe. If you enjoyed this cosmic adventure, don't forget to hit the like button and subscribe to our channel for more explorations into the mysteries of space. The universe is vast and there's so much more to discover. Together, we'll continue to unravel its secrets, one mind-blowing fact at a time. Thanks for joining us on this journey, and until next time, keep looking up. The stars are waiting.